Whoa, didn't see you there. Well, since you're here, let's talk about how free radical halogenation is a gateway reaction. What do I mean by that? Okay, well, here we have an alkane. Not really a lot of functionality on that, right? We don't have any alkenes, we don't have any halides, we don't have any alcohols, we don't have any alkynes, nothing, right? Can't really do a lot with that. Treat it with bromine, treat it with HCl, nothing happens. But we do now have a new high energy type of reaction that will occur on alkanes, and that's free radical halogenation. This is about page 9 of your notes, and is a synthesis question. So essentially here we're trying to get to this diol, this antidiol, plus it's an enantiomer, from just a 5-membered ring with no other functional groups. How would we do that? Usually I say with these synthesis questions to work backwards, right? We have a cis diol, or this is an antidiol. There's only one way that we know that we can make an antidiol. It'd be good to work backwards, and we're going to do that. But one kind of sneaky truth is that anytime we just have an alkane, there's only one reaction possible. The only thing we can do to this is free radical halogenation. There's no other reactions that you can do. So if you have a synthesis question, and the first thing on the left side of the arrow is an alkane, only thing you can do is halogenate it. So that's going to be our first step. So if we treat this cyclopentane with Cl2 and light, that is going to add a chlorine to that molecule. Now we have a functional group to play with. Now we have something that we can change around to get to our antidiol. So now some of you might be very capable of working forwards here. Some of you might want to work backwards. It doesn't matter. Whatever way works for you is great. But I generally work backwards. At the product at the end, we have an antidiol. The way that we get to that is by forming an epoxide and opening that up. So if we look at what the intermediate structure is before getting to this diol, it's going to be an epoxide. And I have this as wedges. The wedges don't really matter. This is an achiral molecule. So I could have drawn wedges, I could have drawn dashed bonds, I could have drawn no stereochemistry at all. It's all the same thing. But we can open that up either with acid or base and water. So if we have basic water around, that's going to participate in an SN2-like reaction, opening up either that position or that position as a nucleophile, making the enantiomeric mixture of the antidiol. So the next question is, how do we make epoxides? You guys know 2 ways to make epoxides. One is through peroxy acids with alkenes. The other is from alkenes, where you would take the alkene, make the halohydrin, and then deprotonate the alcohol of the halohydrin, which would then do an SN2 reaction on the halide. Because it's a chapter 12 reaction, and that's the one that we're in right now, I'm going to say let's do the chapter 12 reaction. So that would be taking the alkene and treating that with a peroxy acid. So the peroxy acid that I said is the most common one, you see it a lot in your notes, is MCPBA. Again, what's a peroxy acid look like? It looks like a carboxylic acid mixed with a peroxide. And in MCPBA, this is just a phenyl ring with a chlorine on that phenyl ring. So we have one step left. How do we get to an alkene from a chlorine, from an alkyl halide? We have to do an elimination reaction. Elimination reactions, if it's a secondary halide like this one, would compete with substitution reactions. We don't want that to happen. We don't want the substitution to happen. We want to make as high of a yield of this alkene as possible. So we are going to treat this molecule with potassium tert butoxide, which again looks like some positive anion. I said potassium. It could have also been sodium. It's just an anion, so it doesn't really matter which one we use. Then we have the oxygen with the tert-butyl group, and it's a strong, bulky base to do beta elimination to provide our product alkene. So glad I ran into you, because gateway reactions are important, and we can do anything. We can do anything to the molecule that we've learned so far, as long as we can make an alkyl halide. We need that free radical halogenation to get to that alkyl halide from an alkane starting material. So good thing we have gateway reactions like free radical halogenation. Let me know if there are any questions, and I'll see you guys later.